All right, welcome to Calc 2. So good afternoon, everybody. Today we're going to talk about trigonometric substitutions, and that's a little bit different than what we were doing yesterday. Okay, so let's go ahead and share the screen here, and we're going to go ahead and take a look at what's going on. Okay, so this section has to deal with what happens when you have a very inconvenient square root in your problem. Okay, and I'm going to go ahead and let you guys go through the examples that they do here on your own, because I think having them walk you through this thing is an excellent way to learn this thing. And we might just start with something like this. All right. So really the canonical problem here is, you're looking at this as a U substitution maybe. I might be able to break this off into like an x squared and an x over a square root of x squared plus 9, right? We might be able to do something like this. It's not a bad choice, right? Is to do something like, we have integral, nice. We have integral of x3 over the square root of x squared plus 9 dx. And you might want to think about it as like, well, here's an x squared, here's an x, here's an x squared plus 9. And to kind of group them, right, and let a u be this thing, because it'll go away, right? If my u is x squared, eventually, right, I'm going to have to do it twice, clearly, but in dv, x over the square root x squared plus 9, right? We can integrate this, right? We could say let w equal x squared plus 9 or something, and then we have something like that going on. We have a v is equal to 1/2, and we have an x squared plus 9 to the 1/2. Oh, that's going to cancel. Okay. And then we'd have to do it again, right? And then maybe, no, I think just maybe one last time. And that'll work out. So in this case, I think you could probably do this with integration by parts, and it would work out. They want us to do something else a little bit here, and that is to do with a triangle. Okay, so this is just a different technique. I guess we could say something like, maybe you could try integration by parts, and I'll do a terrible math thing here and say, get the solution as an exercise for the reader here. Don't do it. All right. But what we're going to try to do here is you've got a square root, and you don't have a convenient u to get rid of it. You don't have an easy way to get rid of it. Okay. So what we're going to do here is we're going to pretend that we have a triangle. Okay. Because we have that as a Pythagorean theorem. So c is equal to the square root of a squared plus b squared. Okay, so when you see this kind of thing, you're kind of looking at a hypotenuse where you have a square root like this. Okay, if I had a different type of an idea here, let's do this. If I did have a different type of an idea, we could also have a squared plus b squared is equal to c squared, and I could pull one to the other side, right? I could say a squared is equal to c squared minus b squared, so a would be the square root of c squared minus b squared. So this would be one of the sides, and this would be a hypotenuse. So when you have a square root, you could kind of talk yourself into saying yourself do a triangle here. All right. So that's the idea. So I confess that the way I learned this is a little bit different than the way your book shows you. So I'm going to do my best to mimic the way the book does it, because quite frankly, I think it's a little bit more efficient the way your book does it than the way I learned it. But there we go. So what we're going to try to do here, actually, I'll show you a little hybrid of both of them, because I think, just I'm not a good person for like, well, if it looks like this, then memorize this form. Like, no, let's set up a triangle and see if we could do that. Okay. So what I want to do, okay, is we have an x squared plus 9 here. So what I really would like to do is to do something like an x That's a theta, by the way. It's not a 9. And a 3. And then this piece here, right, is going to be my x squared plus 3 squared. Okay, so at this point, so I had a plus in here. So I want to set it up so that the plus is actually my hypotenuse, just like we have over here. So that's what you have to remember, is that when you have a plus, you want to set it up so it's a hypotenuse. But you know, at this point in your academic career, I'm going to guess that you've dealt with triangles several times now, and setting up a triangle to put this together, like you'll follow Pythagorean's theorem and you'll know whether or not you set it up correctly. Okay, and if you don't have good pieces here to match, right, especially what's inside of the square root, then make a different choice. Okay, but we could say something like, hey, the tangent of this angle here is equal to x over 3. Okay, or if I multiply both sides by 3, we can say x is equal to 3 tangent theta. Okay, so that's where they got this substitution from. Okay, now the rule is every time you make a substitution in calculus, you're always going to do x, and then you're going to have a dx next to it, or a u and then a du. Okay, always. Well, you may not actually need it. Okay, that's rare. But anytime you make a substitution, you want to figure out the derivative of that. Okay, so the derivative of tangent, right, that's just secant squared. So we're going to have 3 secant squared theta d theta. Okay, so when I'm going back into my problem here, okay, see, the way I learned this is that you had to, like, more or less match these pieces into these pieces, and just doing it this way is just a heck of a lot easier to work on that. Okay, so capitalizing on the fact that we learned trigonometric integrals yesterday, okay, we have the integral, right, x cubed, that's going to be 3 tangent theta cubed. Be careful with this, with these constants, because that's going to be a 27 when I pull it out here. And then divided by, right, and this is going to be 3 tangent squared, so this is square root 3 tangent theta squared plus 9. And then dx. What was dx? Dx was 3 secant squared theta, d theta. All right. Now we're going to go through and just try to sort all of this stuff out. So on second thought, I think the way I learned it may be a little bit faster, but does require you to be a little bit more on top of things. Okay. So because we would do a some kind of a opposite of a hypotenuse kind of a thing here. Okay. So let's unravel this. Okay. So we have a 27. Okay. Actually, there's. Let me not unravel that just yet. Okay. Kind of want to do one thing at a time here. 27. I have a tangent cubed theta divided by the square root of 9 tangent squared theta plus 9. And then we still have our 3 secant squared theta d theta. All right. I'm going to pull a 9 out of the square root, which really means I have a 3 somewhere, right? So could I say something like this, where we have 27 tangent cubed? I've got a 3. Where'd the 3 come from? What's the square root of 9? All right. And then we have tangent squared theta plus 1. And then I've got a 3 secant squared theta d theta. All right. Okay. So remember our Pythagorean identities, right? We have sine squared plus cosine squared equals 1. What if I divide everybody by cosine? Cosine squared, rather. Then I've got tangent squared plus 1 is equal to secant squared. I wonder if I can see a tangent squared plus 1 anywhere here. Right? That's a secant, isn't it? Right here, it's a secant. I mean, it's the absolute value of a secant. It's the positive one. All right? So what we're going to do is we're going to cancel those. We've got 27. I've got a tangent cubed theta. I've got a tangent squared plus 1 square root. So that's going to give me a secant theta. And now we're going to have a secant squared theta d theta up here, right? And some of that's going to cancel. So I think we did a problem kind of like this yesterday where we have a tangent cubed theta and then one of these left. So I just have one secant theta left. All right, and this is what we have to integrate because we're not done yet. I mean, we're halfway through this problem. At this point, you're probably thinking integration by parts would have been better. But we still have to go back to our x's, don't we? So we've got some time still to go. All right. So let's see here. I've got a tangent and I've got a secant. So if I say, how about we reserve a tangent secant? Okay, why don't we do this? We have a tangent squared theta, and then I've got a tangent theta secant theta d theta. There's probably a number of ways of solving this at this point. So this is the way I saw, but I'm not saying to somebody else that you're going to be horribly wrong because, you know, it's just the way it goes. So let's go ahead and move this over. Okay, so we have tangent squared theta is equal to secant squared theta minus 1. So let's just call this secant squared theta minus 1 times tangent theta secant theta. All right, so what I'm going to do here, so we had one substitution to do this, and now we're going to have another substitution because we got to do a substitution in order to do this one, right? So we're going to say let u equal secant theta, and the derivative of secant is secant theta tangent theta d theta. So here we're going to have integral of u squared minus 1, and then this whole business here is my du. All right, so we end up with 1/3 u cubed minus u plus c. The plus c will be there even after we untangle all of these knots and put it back into the original variable. The c will still just be there. It's just c. Okay, it's constant regardless of what variable we've put it in. All right, so let's see here. We have tangent secant. So what the heck was u? U was secant. So we have 1/3 secant cubed theta minus secant theta plus c. Now we're going to go back to our triangle. So secant theta was what? Right? Isn't that square root of 9 or square root of x squared plus 3 over, right? Secant was hypotenuse over adjacent, right? From the SOHCAHTOA thing at the beginning. When you first learned trig, it was, you know, sine, cosine, tangent. So secant hypotenuse over adjacent, right? Where's my 27? All right. So we have 27 here. All right, so we've got 27. I've got 1/3, and then, all right, that was hypotenuse over adjacent, so that's going to be x squared plus 9 to the 3/2, because that was a square root, divided by, right, 3 cubed minus, and then we have x squared plus 9 to the 1/2, again, over 3, and then plus c. And then we've got to sort out some stuff here, right? Because some of this stuff is going to cancel, some of it isn't. All right, so let's see here. We have 27, and then we have an extra 1/3 here. So we have a x squared plus 9 to the 3/2 over 3. And I've got 1 here and this. So I guess this is a minus 9. Okay, this 1/3 only went with this. So we have 9 minus 9 x squared. So it should be plus 9 to the 1/2 and then plus c. All right, I think that should do it for us for that one. Okay, so I know that's really the long way around for some of these, and I do apologize for that. I always thought these were kind of cool for the fact that we go back to triangles. I always gotta like triangles. Okay, but they do tend to be a little bit on the long side. All right, so that's our thing there. Okay, this one they don't tell us. Okay, they don't tell us. And again, there might be a good integration by parts way to do this, but since we're not in that section, we're going to go ahead and say this is the square root of 9 minus x squared. Okay, dx. All right. Now for this one, okay, remember we have a squared plus b squared is equal to c squared. I got a minus down here, so that looks like an a squared is equal to a c squared minus a b squared, and then a is going to be the square root of. All right, so I'm just looking at this kind of like a template, so I can look at this and say, oh yeah, so look at that. C squared is 9, so why don't we make our hypotenuse 3? Okay, and then b squared is going to be the other side. How about we make that x? Okay, and then when I go sort this out, right, that's going to be 9 minus x squared here, right? Okay. So again, I think the way that I tend to do this is a little bit nicer, but your book will say, you know what, we're going to let x equal something. Okay, so what I'm going to notice here, okay, so here's the other substitution you want to make. So we've done a tangent, and now we're doing a secant. Okay, so again, it's secant over, right, hypotenuse. So we're going to do secant theta is equal to 3 over square root 9 minus x squared. Okay, you could do a couple of other things too. I mean, the sine of theta, right, that's equal to x over 3. Right, so there's no, don't get lost into what everything could happen here. Okay, so we could say x is equal to 3 sine theta. Okay, and then we could go through and do this one. Okay, but the ones you're really interested in is you're interested in making a tangent, you're interested in making a secant, and quite honestly, I think you're interested in making a sine. All right, so x squared, right, that's 9 sine squared theta. All right, the nice thing about the sine, what's dx? 3 cosine theta. The reason why you want to make it sine and tangent is because when I take derivatives, we get positive things and I don't have to worry about negative signs. So there's nothing wrong with saying it can be the cosine. You know, we could swap these. But then when I said theta is equal to x over 3, it would be cosine, right? It would be x, you know, cosine of theta is equal to x over 3 if I swap them. And then when I took my derivative, I'd have a negative in here. So it doesn't technically matter, but you know, for the ease of the problem, we want to make things, you know, have as few moving parts as possible because this is already difficult. All right, so what would I do, right? I have a substitution. Let's go ahead and check that out. Oops, now that'll work. So what we're going to do here is we're going to write down sine squared theta, and then on the bottom here, we've got 9 minus 9 sine squared theta inside of the square root. And then we have a dx here, right? dx was 3 cosine theta. Okay. So remember, okay, that sine squared plus cosine squared was equal to 1. So cosine squared was equal to 1 minus sine squared. If I pull out a 9 here, right? So we have 9 sine squared theta times 3 cosine theta. D theta, there's a d theta here. And this is square root of 9, square root of 1 minus sine squared theta. I kind of did what we did in the last problem, a little bit slower. So you can see that that's a 3, and it does cancel. Okay. Well, what's 1 minus cosine, 1 minus sine squared rather? Isn't it cosine squared? So we have 9 sine squared theta, okay? And then I've got a cosine theta, d theta. And on the bottom, right, we have a square root of cosine squared. Looks a lot like cosine, doesn't it? And then there's cancel. So now we have to deal with what is 9 integral sine squared theta d theta. Hey, we did this one yesterday, didn't we? We said that the cosine of 2 theta was equal to 1 minus 2 sine squared theta. So that's going to be 2 sine squared theta is equal to 1 minus cosine 2 theta. Divide. Okay, so sine squared is equal to 1/2 minus 1/2 cosine 2 theta. Let's use that. So this is going to be 9/2 integral. Pull it out of 1/2. So we have 1 minus cosine 2 theta. All right, d theta. And then we're just going to integrate. Okay, now we're doing the calculus part. So we have 9/2. We have theta. Okay. And then what's the integral of cosine 2 theta, right? Isn't that going to be minus 1/2 sine 2 theta? If I take this derivative, right? If I take the derivative of sine 2 theta, I'm going to get cosine 2 theta times 2, which is going to cancel that, which is what I wanted to go back. But if you say let t, let u, let w, let whatever variable you want, okay, equal cosine 2 theta or equals 2 theta, and dt is equal to 2 d theta, and that's how you're going to put this 2 in here. You do go right ahead and do that. Do not let me stop you. Don't let anybody stop you from doing that. That's how you, if that's what we need to do to get the right answer, then that's what we're doing. All right. I want you to be real confident in yourself saying, hey, I need this little intermediate step because it makes me happy and I know where I am. You go right ahead and do it. All right. So we've integrated, right? And now we have to untangle all of this stuff again. Okay. What's sine of 2 theta? I don't have a 2 theta up here, do I? My triangle, do I have a 2 theta? No, I don't have a 2 theta. So what we're going to do here is we're going to say this is 9/2. This is theta minus 1/2. Sine of 2 theta is 2 sine theta cosine theta, isn't it? So that's going to cancel. So we've got 9/2. Here's theta. Here's minus sine theta cosine theta. Right? Now I'm going to go back to my little triangle here. There it is. And then we're going to just go ahead and read these things off. Okay, what was sine theta? Sine theta was x over 3, wasn't it? So this is 9/2. This was x over 3. What the heck was cosine theta? Cosine theta was square root of 9 minus x squared over 3. All right, I'm sure that's a delightful thing. What's theta? Well, if I know that the sine of theta is equal to x over 3, okay, pick an easy one. Okay, well then theta is equal to inverse sine x over 3, isn't it? So we're going to have 9/2. We're going to have sine inverse x over 3 minus x root 9 minus x squared. Again, all over 9 here. Oh, plus c, right? Plus c. Okay, so that's our journey, okay, for doing these things. All right. So they factored through the 9 there. Okay. So the most important thing here, right, is getting the your little triangle sorted out so that this will all work out. All right. So this one, a squared plus x squared. Okay. So we're going to integrate. So what's this problem again? It was a squared over x dx, a squared plus x squared to the 3/2. I already have a dx. We're good. All right. So again, even though I've got a 3/2 in here, right, there's a basic part of this problem that looks like a squared plus x squared square root. And even though it's straight to the 3rd power, we still have an a squared plus x squared in here. And that's really what we're looking at. Again, if there was an x in here, oh, much, much nicer. But there isn't, so we're kind of stuck. This one, I would not want to do this one by integration by parts either. Because what are we going to pick? Like, we're going to pick this for a derivative. Well, this is never going to get smaller, right? We're just going to go with -1/2. Next one's going to be -3/2, and -5/2, -7/2. Oh, this is never going to fix, never going to work. And I certainly want to integrate this. That's the problem. Okay. And taking it apart, integrating some and taking the derivative of the other, I don't see that being a friendly thing to deal with. So again, triangle. Okay, there's a plus here. That means it's a hypotenuse. If it's a minus, it's a side. If it's a plus, it's a hypotenuse. Okay, so we have an x, we have an a, we have an a squared plus x squared here. All right. So our theta, right? We can say sine theta is equal to, oh no, we can't. We want to say tangent theta is equal to x over a. So x is equal to, right, a times tangent theta. Okay. And the reason why we want x equals is because our next step is that. And I really don't want something like this in here to take a derivative of in order to get my dx and have to simplify and solve. No. Pick the simplest one you possibly can, and that's going to be the right substitution. Okay. So derivative of tangent, right? Secant squared. So we have a secant squared theta, d theta. Okay. So when I'm going to go through and do all of this, okay, we have our, right? Again, the way I would have done this would be like, oh, well, a over, right? I'll show you what I would have done here. So in this one, because it's a nicer one, but this is going to look a lot like the first one. We have a squared, and we're going to have an a tangent squared, and we're going to have to go through that Pythagorean identity and deal with all of this. Okay. So what we're going to have here, integral, and this guy right here. Oh, this is to the 3rd power still. Okay. So we're going to say that we have, I want an a over a squared plus x squared 1 over a. All right. Because in my triangle, right, I could say that cosine, right, is a over this thing. So this whole piece here, let's do a 3, because this has a 3 to it. All right. So this is going to be 1 over a cubed. And then we have a over square root a squared minus x. Oh, it's plus. It's plus. Okay, we got that. So this is a over, this is adjacent over hypotenuse. That looks a lot to me like cosine, doesn't it? All right. Now, what was my dx? Dx is still secant squared. So this is cosine cubed. Okay. Dx was a secant squared theta d theta. Okay. So for me, I think this is a little bit nicer because it gives us a little, it goes a little bit faster sometimes. Not in every case. And when I taught this last year, none of the students came along with me for this. It's okay. All right. So we just end up with a cosine theta d theta. They all use this method where they just went through and substituted. Okay, and it's effective. So even though I'm doing a slightly different thing going on here, it's really going to give you the same answer. I find this way sometimes to be a little bit slower, but it's okay. All right, so this is 1 over a squared. What's the integral of cosine? Right? Isn't that going to be sine plus c? Right, sine theta. I take the derivative, we get back to this. Look back at my triangle. What's sine? Sine is, right, this is 1 over a squared. Sine is x over a squared plus x squared. And we have a plus c. Right? That's the way. Oh, did I? No, I think I'm okay. I put the 3 in. We have that. We're good. We're set. Okay. Otherwise, right, we're putting in secants that we're going to raise into the 3rd power, and then they're still going to cancel with this. So I get 1 over secant, and then that's just going to be cosine. Okay, let's go ahead and do it the other way. Okay, let's just go ahead and do it the other way. So what if I substitute? This is the way the book would have you do it, and it's fine. It's a good method. Okay, I'm not bashing the book on this one. So we have, it sounds like I am, but I'm not. Okay, my dx, a secant squared d theta. Okay, this guy down here. Okay, we have the square root. Well, we have an a squared plus, what's my x? My x is a squared tangent squared theta. And this is all raised to the 3rd power down here. Okay. So we have, here's our a, secant squared theta, d theta. Put theta in there. Below my pre-calc class, now I did that. And we're going to pull an a out of this. Okay, so remember, it's going to be the square root of a squared. It's just a, so we have a cubed here. All right, and we have the square root of 1 plus tangent squared theta, all raised to the 3rd power. Well, going back up a couple of pages, right? It's not worth it. Let's just do it this way. We have sine squared plus cosine squared is equal to 1. Divide everybody by cosine squared. And we get tangent squared plus 1 is equal to secant squared. Can't use an s because it's sine. So it's a square root of secant squared raised to the 3rd power. So here we have, this is 1 over a squared, yeah? And then we have a secant squared theta on the top. And we have, right, this thing here inside the square, this is the square root of secant squared, isn't it? So secant. Okay, I'm being very cavalier with signs here. But this is going to be secant cubed theta. And a couple of these are going to cancel, and we're going to end up with 1 over a squared integral 1 over secant theta oops, don't do 2, just 1, d theta. Okay, and you remember what 1 over secant is, right? That was cosine. And again, we can go ahead and integrate that. Okay, but that's what's going to look like if you do it the way the book prescribes, which is great. If you want to take a little bit shortcut and try to be a little bit clever about it, you can do it this way. But you know, stay safe. Do it the way the book says. It's fine. Okay, it will. It'll work. It'll work beautifully. So don't let me try to encourage you to take a path that you might be uncertain on. All right. So there we go. Oh, this was a definite interval. I should have put that in there. Okay. All right. Oh, it looks fun. Let's try this one. Okay, so we have dt square root 25 plus t squared, 0 to 5. That's what we have. Yep. Okay. So again, right, set up a triangle. This has a plus in it. So what we're going to do is we're going to assume that we have a t and a 5, t squared plus 25. Here's my theta. Okay. And again, I'm trying to, if I had gotten this wrong, and my tangent would look like 5 over t, I don't want to do that because we want the variable in the numerator. So the tangent of theta here, right, is going to be t over 5. Okay? So we're going to say 5. Tangent of theta is equal to t. And again, the reason why you want to put the t by itself and make it as easy of a thing you can get is that dt is equal to 5 secant squared theta d theta. You do not want this weird thing of t over here to take this derivative of where you have a chain rule and product. No, you don't want any of that. You want t. Okay? You gotta think like a physicist here. Make it the easiest one possible. Okay. So let's go ahead and do that. So that's my substitution. Okay, that's my substitution. Oh, by the way, we're just going to go and say theta sub 0 and theta sub 5. Okay. We could, right? We could do something like that. We could say when t is equal to 0, right? Then tangent of theta is equal to 0, and that's going to be at 0. Or when t is equal to 5, right? Then we have 5 over 5 tangent of theta is equal to 1, 5 over 5. So theta would be what, pi over 4. So we could replace that with a 0, pi over 4. Okay, that's fine. Okay, what was dt? It saves us from going back, by the way. So dt, right, was 5 secant squared theta d theta. Okay, divided by, oh boy. So this is going to be, right, 25 plus, what's t squared? T squared is 25 tangent squared theta. Pull the 25s out, so we're going to have 5. Okay. So here we have, right, we have 0 to pi over 4. We're going to have 5 secant squared theta d theta over, see this 25? It's going to come out. We have square root of 25 out here. 5 square root 1 plus tangent squared. Okay. What the heck is tangent squared? So I think we just did it up here, right? That tangent squared plus 1 looks familiar, is equal to secant squared. Excuse me. Okay. So we have 0 pi over 4. We have 5's cancel. We have a secant squared up here. We have a secant. Okay, d theta. Some stuff cancels, so we end up with the integral of secant theta d theta from 0 to pi over 4. Okay. Did you look up the integral of secant yesterday when we did cosecant for that integral? Okay, I hope this is one you should memorize. Okay, secant and cosecant, you should just memorize them, because there is a weird like secant theta plus tangent theta, secant theta plus tangent theta that goes on, and we let this one be our u. Okay, so we're going to say u is equal to secant theta plus tangent theta, and then it just turns out that this top thing happens to be our du. Okay, and then we can just integrate from there. Okay, so we're going to end up with a natural log of secant theta plus tangent theta. Okay, that way, plus c. They're not plus c. We have limits. Okay. So let's see here. Okay, thankfully. Okay, secant of theta is 0. Secant of 1 is yeah, secant of 0 is 1. So at least we have that. Okay, so we have natural log secant pi over 4 plus tangent pi over 4 minus natural log secant of 0 plus tangent of 0. Okay, secant of 0 is 1, so that's natural log of 1. And this is natural log, this is secant of that, that's going to be square root of 2. All right. And then plus 1 minus this one. Well, natural log of 1 is 0. And since I know square root of 2 plus 1 is a positive number, and there we go. We will do more of this next week to play with this a little bit more. These can be involved, okay? These really can be involved. So be careful with these, and like I said, we'll do a little bit more. Last year it was a little bit on the tough side because yeah, students have a big problem with this. The biggest thing to worry about is that equation, and if you're dealing with pluses, then you've just got 2 sides equals this one. If you're dealing with a minus, then one is one of the sides and the other one is the hypotenuse side. Okay, so if you draw the triangle, follow the Pythagoras theorem, it will not lead you astray. You will do okay with it. But I notice when people just try to memorize everything and they say, well, if it's this condition, then it's going to be that formula. Like, please don't do that to yourself. Okay, it's a triangle, for God's sakes. Just work out the triangle. Right. So I'm going to leave you with that. You have a wonderful weekend, and I'll post this afternoon. Okay.
Thanks, Professor.
You bet. All right. Let's stop recording.